For the next talk, we have relational cell morphing, automated verification of relational properties of array programs by Weihao from Monmouth University. Let's welcome the speaker. Thank you.
Hello.
Gaboardi from Koskinen University, and yes, I will present his work, mostly it's Weihao's work, collaboration with other people, also Hiroshi.
I'm sorry, I stole the microphone.
All right. So what I will talk about are relational properties. What do I mean by relational properties? Usually we are interested in analyzing two programs, let's say P and Q, and under some pre and post condition, let's say, but where the pre and post condition relate the input and the output of these two programs. In general, we can consider P and Q, but as a specific case, we can also take the same program under different inputs and under different outputs. And this is what I will do in some of my examples, because it's easier to show just one program. And what kind of property we are interested into? Relational properties have been studied a lot in security. A classical example is non-interference, where we have some low and high security values, and we want to show that if a program, if we give to a program something that are low equivalent, two input that are low equivalent, that they are equivalent on the low values, we have as output also low equivalence. And this guaranteed that there is no flow of information from high security to low security. But this is only one of them. There are many other properties. For example, monotonicity of programs show that if we give a higher value, then we get an higher input, we get another higher output. We can consider robustness, which is a property that say that basically our program is robust to small changes in the input, and we show this by showing that the output don't change too much if we change the input a little. And another property that I'm very interested into is to show that when we change output, the cost of a program, when we change input or when we change part of the program, the running cost or the memory cost of the program doesn't change too much. So some notion of cost analysis that is relational and relative to two different programs. This can be useful, for instance, to reason about optimization and show that optimization are not only correct, but also improve our performance. And there is a very large literature on relational property and in general hyperproperty, and people have developed all the kind of tool that you can imagine, from program verification, from type system to use of interactive proof assistant, automated verification, and so on. And I have also worked on this for a large part of my career. Now, the problem is that many of these tools target languages that are functional, and concerning this workshop, they don't really support arrays in general. Of course, this is not always the case, but most of them do not support array. And so this is what we would like to do. We want to reason about relational property, but for program including array, and we have some desiderata. We would like to have some method that is general, which is able to capture, for example, all the properties I mentioned before, but is also reasoning at a high level, For example, similar to the previous talk, reasoning with types, for example. That's what I mean by high-level reasoning. We want this to be lightweight, so meaning that we don't want to overburden the user, but at the same time, we want to be able to be domain-specific in some sense to the analysis we are doing, and we would like also to have it automated. Of course, this is a long list of desiderata, and we are working on them. So let me tell you about some previous work which will converge a bit in our contribution. So, as I said, there is a lot of work on relational verification. One work that we are interested into is also by my collaborator Hiroshi, is about constraint-based relational verification. In particular, there is a methodology that Hiroshi and collaborator introduced that is to encode the relational property as a predicate constraint satisfaction problem. And these permit to have fully automation, and to encode the complex properties, and in particular also complex. So when we talk about the relational verification, one of the challenge is when programs start to do diverging things, like one program does something and the other program does something completely different. So we usually need to reason about scheduling of different instructions, and this method allows to consider quite complex schedule. So the kind of picture you should have in mind, that this is not really to read, is that we can take a program, we can extract some set of invariant that represent our program and the relational property we want to compute, we want to verify, and then we can try to solve the constraint and find some solution. Now, some downside of this approach is that the low level, that the encoding we need to do is kind of low level. This is represented to extract the constraint satisfaction problem. Basically, we are working with label transition system, so this is not really the high level I was talking about. The scheduler need to be synthesized in the verification, and this can be quite complex, and also this method does not support array. So let me mention another work which actually shares some similarity with the previous talk. So we, me and Weihao and some collaborator did some work before on a type and effect system for reasoning about relational cost for a program that are functional but at the same time have arrays. And we consider this lightweight, although in the next slide I will show you some type and you may say that this is not very lightweight. But at the same time, it's just a type description, a bit similar in spirit to the one we saw in the previous talk. And a key point is also that we develop some abstraction to reason about pairs of arrays. And this is something that I will use also later in my talk. So let's say we have a program. Now what we reason about is with types. And types look something like this. Now, as I say, this maybe doesn't look exactly lightweight to you, but it's very similar. These is a type and effect system based on refinement types, like the one we saw in the previous talk. We have quantification over kind. So you can think about all these as some kind of oh, sorry, you don't see what I'm pointing to. So you can see that the type contains a quantification over several indices. You can think about this as annotation that we need to provide to the type to check the relational property. Now, a key component here is this abstraction that I was mentioning before. So to reason about cost, we identified a simple abstraction, which is basically thinking about two arrays and collect the indices where the two arrays agree. This is a simple abstraction, but it's very powerful to reason, for example, about difference in cost, because the difference propagate. And so keeping track of the difference along the execution, this abstraction is enough. Now, the downside for this approach is that we only work with a relational cost analysis, while we would like more properties. It has limited support for the scheduler I was mentioning before, which represents asynchronous reasoning. And the type checking is requiring some annotation to make it go through. One last work I want to mention is another kind of approach. In some recent work, more or less recent work we did with Dominic, who is also here. We did some work on extending our logic with quantitative reasoning in a very general way, so that we can reason about different quantitative properties with the same tool. And I think the next talk will talk also about grading, if I remember well, which is the notion we use here. All right, so this is all previous work. How do we put this all together? So we come up with a new logic to reason about relational properties about arrays, and it looks like this. When I say logic, what you should have in mind is OR logic, so the calculus of pre and post condition. Usually in OR logic we have given a precondition and our program, we are interested in the post condition. Here we have a bit more. So we have two programs, C1 and C2. But we still have our pre and post condition P and Q, but now they represent a relation and not predicate. Usually in our logic they are predicate. We generalize to relation. This is standard in relational verification. Now the part that is more interesting is we add this relational abstraction, so that we can use an abstraction that is specific to the kind of reasoning we want to do. In the case of cost, for instance, like before, we can reason about differences in arrays, but we can reason about different abstractions. And then we have a quantitative grade to keep quantitative properties. Now, how the logic look like? Horrible, like this, with a lot of assumptions. So, but of course, I don't want to go too much into this. But what I want to emphasize here is, so this is just one rule for update. It's called update 1, which hint already that we have an update 2, which I will show you next. Now, what this rule does is trying to use the abstraction, and you see it in the conclusion, it used this beta. These represent our abstraction. And so we are doing an update where we check if the property we want holds between the two things we are updating our array with. And if it holds, we keep the information in the abstraction. If it doesn't, we use the update 2, so we just keep the abstraction as it is, more or less. Now, this is very heavy, as you can imagine. I didn't show you the while rule. I'm not sure even it could fit in my slide, because it has a lot of assumptions. So the question is, okay, but how can we deal with it? Because we don't want to deal with it manually, so we want to automate it. Now, how can we automate it? This is where the title of my talk start to matter. We use this approach that was proposed by Monmouth and Gonor for reasoning about arrays, simple array, unary properties of array, which is called the cell morphing. So this was a work introduced at SAS in 2016, and the idea is instead of using a theory of array, what we can do, because of course, we could use a theory of array, and that's great. But now, when the property become more complex, using directly theory of array may not work well, may not scale well. So what instead they propose to use another abstraction, this cell morphing, which is the idea basically of using an index instead of the whole array, and a potential value for this index. So there is an index k, you can see there, and the ak instead of the whole array A. And now we use this as a free variable, so we quantify implicitly over them, and we do the verification with them. So it's like thinking about indices in a way that we have a uniform property. So the idea is to track one distinguished cell and split then the loop whether we are in this case or not. The way we extend it is to a notion of relational cell morphing, where instead of keeping track of only one values for an index, we keep track of two values, but not only the two values, also some property, some relation between these two values. This is what this bk here is. So for example, we still then do the verification thinking about the loop, whether we have a hit or we skip, so that simplify loops. So this abstraction allows us to reason about different property, for example, can be instantiated in this way. Now, this is nice, is a simple extension of the previous work, but in practice doesn't really work. So we need to add some additional feature. Like we need to use some prophecy variable to deal with quantitative aspect. We need also to have some predicate to explore different case, and we need to adapt the idea of scheduler. And let me show you how we do this, and then I will wrap up. So our constraint look like this, where we have the relational cell morphing, like I was saying before, but we also have prophecy variables that accumulate quantitative properties. We have we want to deal with arbitrary scheduler, so we generalize also indexes of arrays, and we introduce two new predicates, a predicate for choosing different array in our computation and a predicate for the scheduler. And this is basically the main idea on how we verified. We have evaluated this on several benchmarks, and this seems to work well. Of course, it has still some limitation, especially when schedulers are very complex. We time out, our verification timeout. But in general, it seems to work pretty well. All right, let me summarize. What I presented you is a new logic for reasoning about relational properties for arrays, and the method to automate the verification into this logic. And I think the main contribution are really some kind of, although I had to go fast on this, some novel abstraction that we can use to reason about relational property in an automated way. And with this, I'm done.
Sure, we have like 1.5 minutes for questions.
Can you give an example of the relational properties that you, from some of those benchmarks? Like what kind, like I assume like one of them is obviously like quality, for example, but others, like what are other properties that you
So the four property I introduced at the beginning, those are all, for example, that we have in benchmark. In particular, because let's say, for personal interest, we have been interested in relational cost, but also in robustness. I did several work in robustness. So these two are a property that we investigated quite a lot because we are more familiar with the interesting example. But we have done some monotonicity example and some also some non-interference is like the basic property you try. So also that we have a benchmark for it.
Okay, thank you.
Yeah.
We have time at the end for a 10-minute Q&A.
Yeah.
Right. Let's thank our
you.
speaker, Marco. Thank you.
Yes.